Hi everyone, I'm Thibaut Feneuil, and I'm going to present you the article entitled Threshold Linear Secret Sharing to the Rescue of MPC in the Head. This article is a joint work with Mathieu Rivin. In this presentation, I will show you how we can build more efficient zero-knowledge proof of knowledge thanks to threshold secret sharing when using the MPC in the Head paradigm. Here's the agenda of the presentation. First, I will present you the general principle of the MPC framework. Then I will show you how using threshold secret sharings impacts this framework. And finally, I will give you few applications. Let's start by defining what is a zero-knowledge proof of knowledge. Let's assume that we have a public circuit F. We are in the case where a prover wants to convince a verifier that he knows an input X such that the output of the circuit with input X is some public value Y. The prover will first send an initial message named commitment. Then the verifier will ask some questions, some challenges, for which the prover will provide some responses. At the end of the discussion of the interaction, the verifier will say if it's convinced or not. Such an interactive protocol must satisfy three properties. The first one is the completeness. If the prover is honest, meaning that he knows such an input X, then the verifier at the end of the discussion will be convinced. There is a soundness property, which states that if the prover is malicious, meaning that he does not know such a preimage X, then the verifier must reject the proof most of the time. More precisely, he will be convinced only with negligible probability. Finally, this interactive protocol must be zero knowledge, meaning that at the end of the interaction, the verifier must learn nothing about the input X. The MPC framework has been introduced in this article of stock in 2007. This framework provides a generic method to transform a multi-party computation into a zero-knowledge proof of knowledge. And this transformation is very generic, meaning that it can be applied to any cryptographic problem or circuit. Let us describe what type of MPC protocol we will consider. We consider multi-party computation, which take as input an additive sharing of the secret X, meaning that it takes as input x1, x2, xn, so that the sum of those shares are equal to the secret X. Then each party will take as input such shares, and all the parties which jointly compute the function g, which output accept if x, the shared value x, is the right preimage of y, and will be reject otherwise. We assume that the MPC protocol is n-1 private, meaning that if an adversary sees the computation of all the parties except one, then it will leak no information about the secret X. We are working on the semi-honest model, meaning that we assume that the parties follow honestly the steps of the protocol. Instead of considering peer-to-peer communication between the parties, we will consider only broadcast communication for efficiency. The idea is that the party will take all the party will take the sharing of X as input, and will perform some local computation to obtain the sharing of some value alpha. Then each parties will broadcast their share of alpha. And everyone can recompute the plain value alpha. Then the party can continue their computation, but this time knowing alpha. The idea is we will use this MPC protocol in a black box manner to build a zero-knowledge proof of knowledge, which can a zero-knowledge proof of knowledge for which a prover can convince a verifier that he knows such input X. Here's the transformation. First, the prover will generate a sharing of the value X, the secret X, and then will commit each shares independently. Then the prover will run the MPC in his head, meaning it will emulate the computation of all the parties and will simulate all the exchanges between them. It is why this transformation is named the MPC in the head transformation. Then the prover will send the broadcasted value to the verifier. It will send the value which has been broadcasted by the party during the computation. Then the verifier has to choose a random party I star, and the prover will reveal the computation of all the party except for party I star. And in practice, it means that the prover will reveal the input shares of the revealed party, of all the revealed parties. Then the verifier can first check that the revealed input shares are consistent with the commitment and re-emulate all the revealed parties to check that the broadcasted value are consistent with the input shares. We directly get that this interactive protocol is zero knowledge, since the prover only reveal n-1 the computation of n-1 parties, and since we assume that the use MPC protocol is n-1 private. What about the soundness? If we consider a malicious prover, a malicious prover will proceed as previously, will generate a sharing of a value X, but this time X is not a preimage of Y. So if the malicious prover tries to emulate the MPC protocol in his head honestly, then the output of the MPC protocol will be rejection. So he will need to cheat on the computation of at least one party. But in that case, the cheating will be detected as soon as the verifier has to reveal the computation of this cheating party. The only case where the verifier does not detect the cheating is when the verifier has to reveal the computation of all the party except the corrupted party. So it means that the soundness error of this protocol is 1 over n, when n is a number of parties. To sum up, the MPC transformation is zero knowledge, since the MPC protocol we use is n-1 private. The probability that a malicious prover convinces the verifier is equal to the probability that the corrupted party remains hidden, which is 1 over n. But this quantity is not a negligible soundness error. So we will repeat the protocol 2 times in parallel to obtain a global soundness error, which is 1 over n to tau, and we select tau so that this quantity is negligible. But let's raise the question about the computational cost. What is the running time, the bottleneck in the running time of the prover and the verifier? Let's have a look to the previous slide. I said that the prover need to emulate the computation of all the parties in the MPC protocol, and we will need to repeat the protocol 2 times. So the prover will emulate 2 times n parties, and it will represent the bottleneck of the computation. Indeed, if we try to concrete value, if we replace n and tau by concrete value, we obtain, for example, in this case, more than 4,000 simulations, 4,000 emulations, and this is why it's very expensive, since the prover will need to emulate a lot of parties. Recently, at Asiacrypt this year, a new technique has been proposed, named the hypercube technique, to decrease the cost of the emulation cost. And with the hypercube technique, the number of emulation is 2 times 1 plus log of n. In our work, we propose the number of emulation for the prover will be 2 times 1 plus L, where L is an additional parameter, which is 1, 2, or 3. It's a small constant, small parameter. And so it will lead to a faster emulation than in the previous case. So our approach is, instead of using additive sharing, we will use low-threshold linear secret sharing scheme. For example, the Shamir secret sharing scheme. To share the value x, the Shamir secret sharing schemes consists to uniformly choose a polynomial p of degree L, and which has for x for constant term, the x. To share the value x, we need to sample a polynomial p which has as constant term x, and the shares will be the evaluation of this polynomial p, where the evaluation points are public. Such sharing schemes satisfies the following properties. First, it's linear, meaning that if we want to compute a sharing of the sum of 2 values, each party just need to locally sum the respective shares of the 2 values. We have that any set of L shares of sharing is random and totally independent of the shared value. And we have also that any set of L plus 1 shares enables us to reconstruct all the other shares and the secret. Yes. So we can remark that if we want to keep the zero knowledge property when using low threshold linear secret sharing, the prover only must reveal at most L parties instead of n-1 party. Let's have a look to the consequence on the transformation. We cannot, with a standard optimization, we can use C3 when we use to generate an additive sharing, since each shares are independent of each other. But when using low threshold linear secret sharing schemes, it's not possible, and since the shares will contain redundancy, a lot of redundancy. To commit the shares, we will use a Merkle tree since we opened a small number of parties. As I said, L will be 1, 2, or 3. So we will reveal at most 3 parties. In the previous transformation, we send all the broadcasted value. But when we send all the shares of sharing of alpha, there is a lot of redundancy. So we just need to send L+1 shares. But in that case, the prover just needs to emulate in his head the computation of L+1 parties. And so it will represent a big saving in the computation. Then, as I said, the prover will only open L parties, which will be chosen by the verifier. And then the verifier will check that those parties will check that the open party are consistent with the commitment and with the broadcasted value. But since only L parties is revealed, the verifier just need to re-emulate only L parties. In the article, we prove that if we use this transformation with such threshold schemes, sharing schemes, we obtain this soundness error. In the case where L is equal to 1, we obtain this simplified formula, and we can observe that it's a bit larger than the soundness in the additive case, which is this given by this formula. Let's compare the previous case, the case of the former works with additive sharing and our work. First, the goal of our approach is to have a much cheaper emulation. Then, since we use Merkle tree, we will have a fast verification algorithm, since verifying a path in the Merkle tree is in log of n, while when using a C-tree, like it's the case in the other case, when using additive sharing, it's linear in n. However, since we use Merkle tree, which is twice more expensive than the C-tree in terms of communication, and since the soundness error is a bit larger, we will have larger proof transcripts. Moreover, we have this restriction that when we use threshold linear secret sharing, we must have that the number of parties is smaller than the field size, and it's a big issue when considering small fields. Let us describe a few applications. So if we use threshold linear secret sharing schemes, we obtain new trade-off for MPC-NZ-based zero-knowledge proof systems. As I said previously, we obtain larger proof size, faster algorithms, since the emulation cost is smaller, and we have a fast verification thanks to the Merkle tree. But we also obtain a new trade-off for some post-quantum MPC-NZ-based signature schemes, since it's just the Fiat-Chamic transformation of zero-knowledge proof of knowledge. And so the consequence is we will have larger signature size, faster algorithm, and a fast verification. We can have a look to the benchmark of the SDNZ submission package to the new NIST call. When using additive sharing, the two first lines correspond to the transformation when using additive sharing, and the two last rows correspond to the MPC-NZ when using threshold linear secret sharing schemes. We can observe that we have a larger size, but the signing time is much smaller, and the signing time is smaller, and the verification time is much smaller. Another application is that we can use such a secret sharing scheme to have a batching strategy for MPC-NZ based proof system. The idea is we will share simultaneously several witnesses in Shamir secret sharing thanks to packing, thanks when using packing. And this technique is compatible with several former MPC-Z-based proof arguments as limbo. For example, if we consider a circuit with 2 to 8 gates on this field, we obtain a proof size, a unitary proof size of 6 kilobytes. But if we try to batch several statements, we can divide the global the amortized cost will be around 0.5 kilobytes per proof per statement. So we can gain a factor in this case 10. To conclude, we can replace additive sharing with threshold sharing to have new trade-off using the MPC transformation. And the threshold approach enables us to have fast verification, and it also offers an efficient batching strategy for some MPC-based proof systems. Let us remark that this work has been recently improved in a new work available on ePrint. Thanks for your attention.